launching into week 3 of Math 240. We're going to be talking more about matrices and everything about them, but we're also going to be pivoting a little bit. Pivot variable, get it? Anyways, to more ideas about vectors and stuff, because I feel like we've been doing very heavily matrices topics. So obviously vectors are different types of matrices, but more focused on specifically properties and stuff with vectors. But yeah, so for first, we're doing 3.1 right now, and 3.1 is all about determinants. So if you've done any sort of class similar to this, where you've done anything with matrices, you know what a determinant of a matrix is. The determinant of a matrix is a scalar property, so it's just a number versus a vector or a matrix. So the determinant is a number that you can only calculate for square matrices. So non-square matrices do not have determinants, it's just not defined. And the determinant is kind of just a relationship between the values of a matrix in a certain way. So here is an example of how we calculate the determinant, kind of scaling up for it. So determinant of a 1 by 1 is kind of the arbitrary case, I guess, where the determinant of 1 by 1 matrix we never talked about in this class, but I just wanted to cover all bases. I'm getting ahead of myself. Anyways, so the determinant of a 2 by 2 matrix is determinants are also denoted with straight lines instead of brackets. So if you have a matrix and you're I want to show that I'm taking the determinant of this matrix, I'll put solid brackets around it. Note that these line brackets, line versus brackets, that's different than the augmenting line that we used to augment systems of linear equations from week 2. Anyhow, determinants, for a determinant of a 2 by 2 matrix, you just do AD minus BC, and whatever that value is, that's your determinant. For a 3 by 3 and beyond, we don't have as easy of a computation as that. We have to do something called minor expansion. Again, if you've done a cross product before, for vectors in multivariable calculus or anything, you would have done the determinant of you do the determinant of IJK with those two vectors that you take the cross product of, but in this case, we are doing it with just matrices. So minor expansion, basically the gist of it is you choose a row to expand upon. Traditionally you use the first row. You can do whatever you want. Technically it's the same thing. So you do A, and then you multiply that by the determinant. I'm gonna zoom in a bit. So you take the value of A, and then you multiply it by the determinant of the values that are not in A's row or column. So let me clarify this bit. So if we look at A is in the first row and the first column. So then we're going to take the determinant of the values that are not in that, and that's what we're going to put here. Same thing for B, and then instead we will subtract away B, so subtract B, and then think about this is B's row and this is B's column, so we're going to take D, G, and F, and I, and that's what's going to go in here, and then we're going to go back to adding them where we have C, and we have C's column and C's row right here, and then we're going to include the parts that don't go into there. So I can pick a new color. D, E, G, H. And then we take the determinant of those, which we already defined how to take the determinant of a 2 by 2 matrix. So then each of these would just be that determinant, and then you compute it all out. So that's the determinant of a 3 by 3 matrix. And then if you had to compute the determinant of a 4 by 4 matrix, you would then have a 4 by 4 where you would expand upon the first row, and then you would do minor expansion. But instead, each time you'd have, instead of these 2 by 2s, you would have 4 now 3 by 3s, and then you'd have to do all of this within that. So it's very uncommon in this class for you to have to do the determinant of a 4 by 4 via minor expansion, because it's so much computation and it's not really necessary to prove that you can do that by hand. It doesn't really benefit you, it doesn't benefit people that are grading. It's kind of just unnecessary. So, but that's how it scales up. You can do that minor expansion for a determinant of an n by n matrix. It just becomes more and more computation to be done. Big notes is that the row operations that we discussed from section 2.1 that we performed using Gaussian elimination, those are going to impact the determinant of the matrix. So if we multiply a row, the order of these are slightly different than before, but for the row operation where we multiply a row by a constant, so all the cases where we multiply it traditionally, like we'd multiply by 1 over something to like turn something into a 1 or something along those lines. You're going to multiply the determinant by that value. So just the entire determinant number changes by that number. If we swap two rows, so all the times we've done row 1 switches with row 2, row 3 switches with row 2, that's going to negate the determinant. So it's going to just multiply the determinant by -1. And if we add a multiple of one row to another row, so the type 3 operations where we'd be like row 3 is equal to row 3 plus 2 row 1, that does not change the determinant. So my always advice is if you're like taking a quiz and you can't remember what impact the determinants have on a matrix, if you can just always do type 3 operations somehow, then you'll be fine. So that's the idea of determinants. Here is a bunch of properties to discuss. Again, the determinant is only defined by square matrices. So all of these things are only applied for square matrices. And unlike inverses, every matrix has a determinant. It just depends. It can be 0, which is kind of the equivalent. It's exactly the equivalent of a matrix not having an inverse. But here we go. Okay, so the determinant of the identity matrix is 1, which I think makes sense. In general, determinant, think the product of the diagonal, so multiplying across the diagonal. So I is any identity matrix, the determinant is always going to be 1. The determinant of A times B is equal to the determinant of A times the determinant of B if determinant A and determinant B if matrix A and B both have determinants. So obviously, if the biggest case with this is if A and B are both like n by n's and then AB is an n by n, it's obviously going to always be defined. But there are specific cases where you could say like AB is a 3 by 3, but A is a 3 by 2 and B is a 2 by 3. In that case, this doesn't apply because, like we said, non-square matrices don't have determinants. So this only applies where A and B are square, so n by n's. And obviously that they would have to be the same size n by n because otherwise AB is not defined. You can't multiply out AB if they're not the same size for square matrices. Another thing is if we take the matrix and we multiply the entire matrix by some scalar, so like if we take the entire matrix, multiply it by 5, we scale the determinant 3 to the n where the n is the size of the matrix. So if it's for a 3 by 3 and I multiplied the whole thing by 5, it would be 5 to the 3rd times the determinant of A. I think this kind of makes sense, especially based on what we said here, because it's kind of the same as multiplying every row by a constant, which would mean you just have to multiply based on how many rows you have, which is the size of the matrix. If there is a row or a column of all zeros, so matrix can be really filled, it can be a huge matrix, but if there's an entire row of zeros anywhere or an entire column of zeros anywhere, the determinant is always going to be 0. Just think product along the diagonal, and that means that there's a 0 along the diagonal, and that would make it be 0. The determinant of upper and lower triangular or diagonal matrices is the product of the diagonal entries. Recall that upper and lower triangular matrices are matrices where you have only values along the diagonal or below for lower triangular, and then for upper triangular, you only have values along the diagonal and above. And then obviously, if there's a 0 along the diagonal, then that entire product is going to be 0. The determinant of the matrix, when you take the transpose of a matrix, it doesn't change its determinant. So you can take either determinant of A to the T is equal to the determinant of A, and the determinant of the inverse of a matrix is equal to the reciprocal of the determinant. So like this just means 1 over determinant of A, which is kind of interesting. Okay, now to some really cool things that's kind of a synthesis of what we've been talking about for the past couple weeks. Okay, so the determinant of a matrix tells us a lot because all of these things are kind of related to each other. So if the determinant is 0, so like we said before, when it's equal to 0, here's a bunch of ways to tell if it's going to be equal to 0 or not. But if it's equal to 0, this tells us that the reduced echelon form is not the identity matrix. This makes sense because that would mean that there's like zeros along the diagonal, We wouldn't have full pivot variables. We would have at least one free variable. So the reduced echelon form is not the identity matrix, which then, as we talked about in 2.2, means it's non-invertible. So that means that the inverse does not exist, which, like we said, if we have at least one free variable, that means we don't have full rank. That means we have rank is less than n. And when something has the rank that's less than n, we always are going to have some homogeneous solution, some kernel, null space. Remember, those are all the same thing. Basically, like, recall that when we were solving for the null space of a matrix or the kernel or the homogeneous solution, we always set it equal to whatever the free variable was, right? So in this case, this is telling us we have a free variable, so we know there's going to be something in the kernel. If we don't have free variables, we don't have this column vector, right? There's nothing to put there. And like we said in 2.2, that makes it a singular matrix. It's just a term. So then if the determinant is non-zero, going back, we're switching all of these. That means that the reduced echelon form is the identity matrix, again, which tells us that the inverse of the matrix exists. It has full rank. The kernel, we say, is kind of like the trivial solution, is what we call it. Trivial solution. Which means it's empty. You can say it's empty. It means it's set equal to 0. It kind of just means that. So the trivial solution inherently for a system of linear equations is like where. So the homogeneous solution, right, is for any system where you have A and you have X and you have the 0 vector, right? And we're trying to solve for this. The trivial solution tells us that we will always have a solution if we just set this entire thing to 0, which is true. If I just plugged in 0 for everything, I'm going to be equal to 0. That's just inherently true. So that's what we consider the trivial solution, because it's like, yeah, sure, but it's not contributing anything to our understanding of the system. So if the determinant is not equal to 0, that tells us that we only have the trivial solution. So we only have the like cop out where if you set everything equal to 0, it's going to be true. And that's considered non-singular matrices. Okay, let's do a few examples of calculating determinants. These are really straightforward. Taking the determinant of a 2x2 is as simple as it gets. So you just do this. So this is 10 minus 54, which is negative 44. And then here, we're going to do some minor expansion. Quick minor expansion. I'm just going to. So I can just skip to calculating the determinant of the like inner matrices. Okay. So now we got 4 times, all right, here comes my algebraic mistakes. 30 minus 6 is 24. Right, so then 54 minus 21 is 33. Plus 2, 18 minus 35 is negative 17. And magically, that all becomes negative 169. So these just both tell us, okay, it's non-zero. That means the fact that it's negative doesn't really matter too much to us in this class. It tells us a little bit about something that we'll talk about later, like linear transformations. That's week 5, but not too important right now. So just knowing that it's 0 versus non-zero is our biggest concerns, which these are both non-zero, which tells us all of these things are true. They have an inverse, they have full rank, blah, blah, blah. Knowing that when the determinant is not equal to 0, I think, because objectively, it's easier to solve for the determinant of a matrix than to do the reduced echelon form. It's much quicker, and it's going to be easier and less prone to mistakes. Personally, if you're taking a quiz, if I were you, and you get the reduced echelon form, and you think, if it's not the identity matrix, and you thought it was going to be at the identity matrix, calculate the determinant. So you know that if the determinant is equal to 0, it shouldn't be the identity. And if it's not equal to 0, it should be the identity. It's just a good relatively quick way to check your work. Okay, so now we're going to talk about an example of like relationship between determinants and invertibility, like I said. This one wants us to find the determinant of this matrix. Again, not too bad. 0, 4, 1. 1, 4. Minus -1, so +1, 2, 1, minus 0, minus 0, and then this, I'll just write it out, but it doesn't matter because it's 0. So 3, 1 minus 28 is 27, plus 2. This 27 times 3 is 81. Yes. Plus 2, 83. I feel like this is not 83. Give me 1 second. It's because this is supposed to be a negative. Right. Oh yeah, this is 1 minus 28, so it's negative 27. My bad. So that gives you negative 81 plus 2 is negative 79. That's the determinant of this matrix. In terms of lambda, what is the determinant of B? So the determinant of a lower triangular matrix, we know this is lower triangular because there's only values along or below the diagonal. It's just the product of the diagonal, which is just going to be 1 times lambda times 5. 5 lambda. In terms of lambda, what is the determinant of AB? Like we said, determinant of AB is equal to the determinant of A times the determinant of B. It's also worthwhile to note that this means that the determinant of it's equal to determinant of B times the determinant of A because the determinants themselves are scalar numbers, so we come back to our conventions of scalar multiplication where we can switch back and forth. But determinant of this, so determinant of A is negative 79 times the determinant of B, which is 5 lambda. So 79 times 5 is negative 375 lambda, and that's our determinant of AB. For what value of B of lambda is B invertible? Again, invertibility is associated with whether or not the determinant is 0. For something to be invertible, we need the determinant to be non-zero. So for what value of B is B invertible? So B inverse exists. The determinant of B is just 5 lambda, like we said. So that just means when this is not equal to 0. So any values that don't set this equal to 0, which is a lot. So just where lambda, I guess, is not equal to 0. Cool. Few worksheet questions. So starting with the first question is it's asking us to find the determinant of a 4x4 matrix. So determinant of 4x4, as we discussed, is going to be difficult without simplifying it a little bit, and because we don't want to do minor expansion. So we want to use row operations to simplify this into something we can compute the determinant for more easily, which would look like an upper or lower or diagonal, an upper or lower triangular matrix or diagonal matrix, because that's always the product of the diagonal. So ideally we want to make this into a upper or lower triangular matrix or a diagonal matrix. So the first thing I want to do, so I need to make this an upper, I want to make this upper triangular matrix. So I want to preserve everything along the upper triangle. So I need to get rid of these values. So first thing I want to do is get rid of them by doing row 2 is equal to row 2 minus 2 row 1, and then row 3 is equal to row 3 plus row 1. So let's do that. 1, 2, 3, 0, 0, 2, 0, 7. Okay, so row 2 is equal to row 2 minus 2 row 1, so this is 0, 6 minus 2 times 2, so 6 minus 4 is 2. 6 minus 2 times 3, so that's just going to be 0. And then 1 minus 0 is just 1. And then negative 1 plus 1 is 0. Then 0 minus 2 times 2 is negative 4. then, oh wait, no, sorry, I'm not subtracting them now, I lied. -1 plus 1, 0 plus 2, 0 plus 3, and then 3 plus 0, so 3. And now I'm doing great. I know that I want, again, my upper triangle is this quantity, so I want to get rid of anything that's happening here. So I want to get rid of these two 2's. And I can do that by using the values in the second row. So row 3 is equal to row 3 minus row 2, and then row 4 is equal to row 4 minus row 2. So row 1 and row 2 stay the same, 1, 2, 3, 0, 0, 2, 0, 1. Then row 3 is 0 minus 0, 2 minus 2, 3 minus 0, 3, 3 minus 1 is 2. And then my fourth row is also row 4 minus row 2, so 0 minus 0, 2 minus 2, 0 minus 0, and then 7 minus 1 is 6. Amazing, now I have that upper triangle. Looks like this. That's what belongs in there. And so my determinant is going to be the product of the diagonal. So it's just these values multiplied together. Determinant of A is 1 times 2 times 3 times 6. And the biggest thing, remember, is we did row operations. So we changed the matrix somehow. We have to make sure that that didn't change the determinant. Looking at all of our row operations we did, which is why you should really write them down every time you do them so you can go back and check, is I did these 4 row operations. They were all type 3 operations, which we remember does not change the value of the determinant. So if we did any other row operations where it was like we multiplied a row by some value or we swapped 2 rows, we would have to do that implication with the determinant. But here we don't have to because we didn't do any of those. So the determinant is just 2 times 3 times 6, which is just 36. Cool. Next up, we have variables. Honestly, that gets a lot more confusing, but we're going to do the same process and hopefully we'll lose our minds. So here, I want to get an upper triangular matrix. So I'm going to first turn these both into zeros. So I'm going to do row 2 is equal to row 2 minus t row 1, and row 3 is equal to row 3 minus t squared row 1. So being very careful in what I do. So 1 t squared, and then row 2 is row 2 minus t row 1, so that's going to be t minus t here, which is going to be 0. My second value is 1 minus t times t, so that becomes 1 minus t squared. And then I've got t minus t squared, so that becomes t minus t cubed. Then my third row, the first thing obviously should go to 0 because it's t squared minus t squared times 1. Then I've got t minus t squared times t, so that's just going to be t minus t cubed. And then my last value is 1 minus t squared times t squared, so 1 minus t to the 4th. Again, I'm trying to get an upper triangular matrix, so the last thing I need to get rid of is this guy. So I need to figure out what can I multiply to get rid of it. So I can look at the things that are happening in that column, and I can see that this becomes this if I just multiply it by t. So that's what I'm going to do. I'm going to subtract away t times row 2. So R2 is equal, or R3 equal to R3 minus t times row 2. So 1 and 2 don't change. 0 t, nope, t squared. 0, 1 minus t squared, t minus t cubed. And then I'm going to do the last row, so 0 minus t times 0, so 0, t minus t cubed, so t minus t cubed, minus t times 1 minus t squared, that becomes 0, and then my last thing is this last column, so 1 minus t to the 4th, minus t times t minus t to the 3rd. So that mess, 1 minus t to the 4th, minus t squared plus t to the 4th. So these cancel out, leaving us with 1 minus t squared. A little bit of polynomial math for you. And then again, we made an upper triangular matrix because we only have values along the upper triangle, which the determinant is always going to be the product of the upper triangular matrix, the diagonal. So the determinant of A is just 1 times 1 minus t squared squared. Now they want us to use that the determinant is multiplicative to prove that the determinant of the inverse of a matrix is equal to the determinant times -1. So just asking us to prove this property. Using the determinant as multiplicative, they want us to show, because we know the determinant of AB is equal to the determinant of A times the determinant of B. We also know that the determinant of the identity matrix is 1. And we also know that if we take a matrix A times its inverse, it's always going to be equal to the identity matrix. Putting these two things together is we have the determinant of A to the inverse is equal to the determinant of I, which is equal to the determinant of A times the determinant of A inverse. So just kind of putting those two ideas together. And we know that the determinant of the identity matrix is 1. So we can set this equal to 1, meaning we can then, remember these are two numbers, so we can divide by these because they're actual numbers. So we have the determinant of the inverse of A is equal to 1 over the determinant of A, which is the same thing as determinant of A to -1. We proved that this is true. And the last thing, the last worksheet question is kind of confusing, so we'll try to do it as well as possible. So let A be a K by N matrix and B be an N by K matrix, and assume that K is less than N. For our intents and purposes, I'm going to give those specific values so it's easier to conceptualize, but it does scale up arbitrarily for any K for any N, assuming that N is greater than K. So let's say that K is less than N. So A is going to be a 2 by 3, where K is 2 and N is 3. So I think it really helps to see this 1, 2. So this is what the size of A looks like. Then we have B, which is then must be a 3 by 2 matrix. So this is N, this is K. And I've got 1, 2, 3, 2. So just look at the size of them. And then obviously it would scale up for bigger numbers. Prove that the determinant of BA is equal to 0. And again, we can't use anything about this property because B and A are not square, which they made sure we knew that because N must be greater than K. So we can think about the fact that what does it mean for the determinant of something to be equal to 0? Going back, determinant being equal to 0 tells us all of these things about a matrix. It tells us that, especially, it has a non-zero null space. It has a kernel, and it has a less than n rank. So in this case, essentially the best way that they like to prove this is that we need to show that BAX equal to 0 has non-trivial solutions. So if BAX, which is the same as just AX equals 0, the idea of it, so just solving for the null space, if this has non-zero values, that tells us that the determinant of BA must be equal to 0, because if it has a null space, that means it has free variables, which means it doesn't have full rank, which means that the reducible echelon form is not the identity, which means it's non-invertible, and the determinant is equal to 0. So it all is connected based on those ideas. And we can prove this because we can show that AX equals 0, so we take this and we move the parentheses where we have AX, so just thinking about AX right now equals 0, we know that AX equals 0, so this is my AX equals 0, thinking about this system, we know that AX equals 0 must have non-zero solutions for this system because we have 3 variables and 2 rows. Every pivot variable must have its own row. That's the whole point, right? That's the definition of a pivot variable, is it's the leading one in every row. If we have more columns, so we have more variables than there are rows, then we must have at least one free variable. We could have two free variables, we could have three free variables, but we must have at least one. So like in this case, this is x1, x2, and x3. They can't all be pivot variables. There's not enough room. There's only 2 rows. So one of these must be a free variable. It doesn't have to be x3. It could be x2, it could be x1. But one of them must be a free variable, which tells us that ax equals 0 has a non-zero kernel. Since that has a non-zero kernel, that means that ax equals 0 has a non-zero kernel. And then when you multiply by a matrix like this on the left, it's going to absorb the kernel from before. So like multiplying, so imagine we had this system already. We know that there must be non-zero values. When I multiply this by b, it's still going to have those values, but it is going to have potentially more. It's never going to have less. So BAX, we're saying now, must also have non-zero values because it's going to contain the non-zero values from ax equals 0. So that's kind of the definition of why the determinant of BA must be equal to 0, because BAX equals 0 has non-zero solutions. And then what about AB? Can it be 0? Can it be non-zero? This one is less specific because we're not as constrained by the value. So instead, here we have A, so we have ABX is equal to 0. So trying to think, can we use the same logic? So looking at BX equals 0, B is this 3x2 matrix for us, right? And again, it's just any matrix where the number of rows is greater than the number of columns. So 1, 2, 3, 2. Looking at this, we could have a kernel or we could not have a kernel. It depends, right? Because we have enough rows for every variable to be a pivot variable. So we could have, where we have like this could be our reduced rational form of B, but it could also not be. It could look like this. We don't know. It just has more opportunities to have free variables or not have free variables. So we don't know anything about the kernel of B. So we can't say anything about the solution set of Bx equals 0. Therefore, we can't say anything about the solution set of ABX equal to 0. So their definition for the people that wrote this question is that it can be 0, it can be non-zero. Examples of when it is going to be equal to 0 is if either of the matrices is the 0 matrix. And then we can also say that if A is an identity matrix, is a pseudo-identity matrix. So if A is like 1, 0, 0, 1, 0, 0, and B is the transpose of that, so let's say 1, 0, 0, 1, 0, 0, then AB would be the identity matrix, and then they would have a determinant of 1. So it can be 0 if we set either of the matrices to be the 0 matrix, or it can be non-zero if this. It's also, there's many other instances where it's not 0 or 1. It can just be a number, but these are specific examples of how it can be 0 or how it can be non-zero. But yeah, that is section 3.1, the idea of determinants. We'll be using determinants not in 3.2, but in a lot of stuff following. So 3.2, we're kind of taking a side road and then getting back to matrices back in week 4 and beyond. So determinants are fun. I feel like it's a good break for your brain because they're pretty chill. And I think that this result of how determinants are related to stuff we've been talking about before is pretty satisfying. So I enjoy this section. I think it's pretty great. That's 3.1.